All right, Stephen, we got some quantum sequences to get through too.
I
For,
think I feel good about these. Decoherence is our first post here. It's been a while since we've done these.
that was actually one of the things I was thinking when I was reading through these a couple nights ago. When we read two of these over 2 days, like one a day, the concepts are still fresh in your mind. You can build on knowledge you've had, and you keep going, and everything works out. Where after a couple months, you're solid. Now doing them like two every. Let's be honest, every 4 weeks, because we've had a number of long episodes, so we kind of been skipping every other one. So, like having one post every other week on average, the concepts do not stick in your mind for that long, or they don't for me anyway. And every time it's a bunch of review, and I feel like I'm not really building much. It almost feels like this was a mistake to do it with so many gaps between the things, and we should have just all done it in one big thing, maybe.
Next time.
Next time, right? Yes.
Next
when
time.
we do this
Next time
again
we
in
start
a
a
century.
podcast 10 years in. Yeah.
Yeah.
That's the thing is it links back. It's like shit. Yeah, I got to refresh my brain on that. But anyway, the first one on decoherence. Yudkowsky has a fun way of writing, but I don't want to just read the post. I'm going to kind of just give my quick rundown of it. Decoherence is the process by which quantum systems come to exhibit classical like behavior. And I think the key points are basically like what is quantum entanglement, how entanglement forms, what's decoherence, and why decoherence matters. Then there's the bit about thermodynamics and classical hallucination, which leads into the next post. He starts by saying like quantum independence exists when amplitude distributions can be factored into separate sub-distributions. Quantum systems interact, or when they do rather, the independence is often destroyed, creating entanglement. And this isn't the ghostly link that I know that I definitely had like kind of in my image of, oh, this electron outside of Pluto is entangled with this one here in this, particle accelerator. It's not that.
Mm-hmm.
It's just the absence of factorizability.
So, okay, what does the absence of factorizability mean?
Factorizing here actually just means what it means in algebra. That it's when, factorizing basically just means that like whatever 3 and 5 are factors of 15. You can break them down into smaller parts. And so when a quantum system can be broken down into independent parts, they're factorized. And that means in the quantum realm, I'll say in Ant-Man terms, the wave function or amplitude distribution of the entire system can be written as a product of separate wave functions for each subsystem. And if it can't be broken down anymore, then it's not factorized.
All right, so he gives this example of a light particle and a heavy particle, and they're oppositely charged. So the light particle, when it gets closer to the heavy particle, is going to be attracted to it. And if we recall back to our shaded graph that shows where particles could possibly be, where the dark shaded areas are where it's more likely to be, and the light shaded areas is where it's very unlikely to be. Like if you think of if this heavy particle has two places where it's very likely to be, then those are dark shaded. And when the light particle gets closer to it and gets attracted to it, then its shaded areas are going to merge and become in the same two places that the dark particles are, because that's where it's most likely to be. Wherever the heavy particle is where the light particle is drawn to. So their two shaded graphs tend to merge like that because their locations will be correlated, and that is entanglement, more or less.
Right, that makes sense, as far as my understanding.
Oh, and an important part that he wanted to draw attention to was that he was using the words, there's a possibility of, both particles here or both particles there, and that is the dark blobs, but wants to point out that this is just language. It's in both places with certain probability mass, certain shadings in the graph, for example, and not that the particle is in. It's not that the particle is in one place or the other, and we don't know which. It's that it's distributed with different amplitudes across those two places.
Right. This is different than me, doing that cup and a ball trick that people do, where I shuffle them around and it's like, all right, where is the ball? Is it under one of these three cups? That's an uncertainty about the map thing. This is like, no, the map, but it has a probability. Like that's how it actually is. It is 1/3 chance over here rather than just the odds of being under this cup are 1 in 3.
Yeah, it's got 1/3 of its probability mass in all three places.
Right.
He points out that if 20 other particles come by and all these things do a dance, many of the final configurations have received amplitude flows from both the initial blobs. So everything is all kind of mixed up at both the blobs, the ones that were 50% here and 50% there. Both blobs affected all 20 particles.
Right. And decoherence is, my understanding was that the interaction creates a wider separation between the blobs of amplitude and configuration space.
Let's take a second before we get to that point because he gets a smaller example first.
Oh, sure, entanglement.
Where both blobs are interacting with all 20 particles only happens when both blobs in the initial system are close enough that their evolutionary paths can slop over into each other and affect things. But he says it's not that uncommon for blobs to get separated by a wide space, and says, for example, imagine that there is some third particle, and these two particles that are already entangled with their two blobs of probability mass are there, and the third particle comes by. That third particle entangles with them and rolls down the hill. In the case of one blob of amplitude, it rolls down the hill on one side of the hill. In the case where it's interacting with the other blob of amplitude, it rolls down the hill in the other direction. And so where the third particle is in drastically different locations in these two amplitude blobs. And since the entanglement with that third particle has made these two amplitude blobs very different from each other, they are now much further apart than they used to be. And that is the concept of decoherence.
Yeah. Decoherence occurs when an entangled system, like the two particles that you're describing, are either both here or both there, interact with more particles, and this creates a wider separation between the blobs of amplitude in configuration space. So that's what it means by being further apart on that drawing. And as more particles become entangled with the original system, the distance gets between the amplitude blobs increases, and when they're sufficiently separated, they stop interfering with each other. That's when they decohere. And this is important because decoherence makes quantum systems appear more classical because separated blobs behave independently.
Yes, now they're too far away to slop over into each other, and when the 20 particles come by, now their two blobs are far enough away that only one of them interacts with the 20 particles and not both of them.
This is why, A Wrinkle in Time and Men Who Stare at Goats was misguided. Yes, there's a chance that if you walk towards the wall, you'll walk through it, but the chance is so close to zero, I'll bet you my life and the life of everyone I love that'll never ever happen in 100 billion years, because those quantum states aren't coherent with each other. In fact, we're talking at a scale way above that anyway when we're just talking about walls and people. But do you remember that scene from Men Who Stare at Goats?
Yeah, I do.
And then A Wrinkle in Time had some similar bullshit.
The key to decoherence is that once things are far enough apart, then human physicists can just think about one blob at a time without worrying about how the other blob interferes with things, because they're so far away that you can just think of them as separate things.
Yeah. Is this where he also mentions qubits and quantum computing?
Yes, I think it is.
All right, well, I'm going to just go ahead and say pass. Quantum computing is not part of the subject of this LessWrong sequence post summary.
Okay, great.
Because there's too much there. Yeah, I'm also not equipped to understand it.
So the part about walking through walls or whatever because of quantum effects, the thing that he points out is you can't just make the blobs get closer to each other again by themselves. You would have to also revert all the interactions that made them go further away from each other. You would have to reverse those as well, which means in this case, the third particle would have to go back up the hill to where it was before. It's not physically impossible for it to happen, but the laws of thermodynamics, the second law of thermodynamics specifically, says that it won't. It is the literal metaphor, because it's not a metaphor, it's just actually the same thing as unscrambling an egg.
Right.
Like, all the particles in the egg could go back to where they were, but they're not gonna. The same way, you could get these blobs back together theoretically, but it's not going to happen because every single interaction on every single particle that had any interactions all has to revert to the state it was before for these blobs to scoot back together. So they are far apart now forever and quote unquote decohered.
Yes. I only have one nit to pick, which is that you said that the second law of thermodynamics says that it won't happen. Won't there is in the sense of 1 in 3 to the 3 chance of it never happening, or 3 whatever, the stupid big number. It's not physically impossible. It doesn't violate fundamental laws. It's just statistically improbable to the point that it will never happen. Like the odds of it slamming back, like of a scrambled egg slamming back together into the form of an uncooked regular egg, it doesn't violate the laws of physics. Nothing has to appear out of nowhere or anything like that. It just
it violates the second law of thermodynamics, which is slightly different.
Well, that is a law of physics. But it's not a fundamental law.
It's a way of describing what happens when physics is working, but I don't think it is a law of physics the same way that forces mass times acceleration is a law that just describes what happens with particles.
Huh. I'll have to noodle on that because I think, isn't that the first law of motion? Or no, wait, sorry, you're right. The first law is actually just about inertia, and the equation is the underlying math. You're right. So,
Right.
okay, yeah, no, fair enough. Consider my nit unpicked. I like the classical hallucination thing that talks about the end. That decoherence is the third key to recovering classical physics
Hmm.
because now physicists and people can treat blobs independently without worrying about interference, and individual blobs appear entangled and less entangled internally. And this makes the quantum world easier to understand in classical terms, so obscures quantum computing potential. Decoherence is what lets us look at stuff like, I was going to say actual physics. Excuse me. Actual physics is this. I'm going to say like easy physics.
That brings us to the so-called Heisenberg uncertainty principle.
Yes.
I'm lost, Stephen. This post depends on the reader knowing wave mechanics and knowing calculus. And I do not know wave mechanics, nor do I know calculus. So this is just over my head.
Yeah, I skipped the math and just went to the language part of it.
Yeah, but you can't. The language is the language of math. Like he talks about taking factorizations and integrals, and you can't fully understand this without knowing the math. And so I am just going to cop to it and say that I do not fully understand this.
Oh yeah, I think I've said that from the outset. I don't fully understand any of this stuff. I don't aim to. I hope to be able to be slightly more able to follow a conversation, but I'm not going to be leading any seminars on the subject. I didn't get the math, but I'm aware of the Heisenberg uncertainty principle, and it was nice to have this slap in my face that it was improperly named.
Yes.
In quantum physics, knowing the position amplitude distribution completely determines how it'll evolve. Unlike in classical physics, the particle's position and speed aren't separate facts. In quantum mechanics, they're inherently connected, the position and speed. And like my vague high school understanding of the Heisenberg uncertainty principle was that you can't know both the position and trajectory of a individual particle. But what Yukaski is saying here is that no, it's not that you can't know the both. It's that these aren't separate facts. They're inherently connected. Where its trajectory and its position.
Yeah.
Because like you can separate that when you're talking about like a car driving down the street.
Mm-hmm.
Like it's over there and it's heading this way are two different sentences.
Mm-hmm.
But that just apparently isn't the case when you're talking about particles at the quantum level.
Yeah, apparently.
Yeah.
This goes deep into wave mechanics, and it does say that wave mechanics, one of the basic tools of wave mechanics, is taking apart complicated waves into a sum of simpler waves. So, like, if you got a whole bunch of bulges and squigglies and all sorts of pitch and diameter, you can take that big ugly wave apart into a number of smaller waves that get added together to make it that big ugly one, which actually I think we are probably both familiar with because we've done waveform editing before when we do podcasts, and you can see sometimes where you add two simple waves together, how it makes a bigger, more complicated one.
Yeah, the things I took away from this post again wasn't so much the math, and like I realize that's half the point. But Yudkowsky in the rest of the sequences doesn't expect his readers to become mathematicians, and so I'm trying to just get the stuff out of this that I can get without being a mathematician. And this obviously these posts like are more math heavy, but I think there's still stuff to get. Like the observer effect. Remember back in the day, you maybe heard about the people thought that quantum systems decohered when looked at by a conscious observer.
Yeah.
The decoherence perspective and observer effect perspective are dual explanations of the same phenomena.
As you were saying, like this is just one wave function, the part of what the particle is doing. They're not two separate facts, but you can look at them, simplify them into two different waves that are the position and the momentum. Because of this, now here's the words I do not understand, that when the position distribution is more concentrated, when that wave bulges more sharply, the integral over momentum helices gets more widely distributed. I don't know what the hell that means, but he assures me that the physical consequence of this is that anything which is very sharply in one place tends to soon spread itself out, that narrow bulges don't last.
I guess I'm just trying to picture like a very, very high probability density quantum state doesn't last very long. I think that's what he's getting at.
I don't think so.
No?
Because he's talking about bulges in wave forms when they've been simplified into smaller subsets. I just don't understand. Like, okay, here's a sentence that I think if I understood the words in it would make a light bulb go on in my head. You might find it convenient to think, A narrow bulge has sharp changes in its second derivative. And I know the evolution of the amplitude distribution depends on the second derivative. So I can sort of imagine how a narrow bulge might tend to propagate off in all directions. That sounds very logical, but I don't know what the words in that sentence actually are pointing to. So I don't know what semantic meaning to take from this.
Yeah, I'm kind of just learning enough to guess the teacher's password on these.
Okay, so this is what he says the consequence of this is. If S is highly sensitive to X's exact location, the result is to decohere X's position distribution into two non-interacting blobs. The two non-interacting blobs thing harkens back to the post we were just talking about. And over time, each blob spreads itself out again. One thing this has an effect in the real world is like a slit experiment. All the positions, except a very narrow range, have decohered away from the blob of possibilities of the photon goes through the slit. So within that blob, the position amplitude is concentrated very narrowly, and thus the spread of momentum is very large.
Yes.
Again, that's a sentence that, like, cool. That sounds like a reasonable thing to say, but again, I don't know. It's not connecting to things in my head.
Yeah, it seems like a perfectly cromulent sentence to me, but I can't expound on it. So that's kind of why I just was jumping further ahead, where he's talking about the Heisenberg student confusion principle that definitely, absolutely, positively does not say that knowing about the particle or consciously seeing it will mysteriously make it behave differently because the universe cares what you think.
Right.
And this for my, and where did I learn this? Because it wasn't originally from Yudkowsky. It might have been, it was probably like A Brief History of Time or something. Or Bill Bryson's A Short History of Nearly Everything. But I'm bringing all this up because the history of science, back when they were talking about this initially, this was a seriously considered position.
I remember.
So, well, you remember hearing about it, but
yeah, I certainly wasn't there doing the experiments.
You're like, who said I've been alive forever?
Yeah, right. I mean, like what he's saying is that things that are extremely sensitive like that will decohere a very tiny blob away from the rest of the possibility space. That has implications for how that tiny blob acts. And physicists tend to construct very sensitive instruments that slice apart these tiny amplitude distributions from the main blob into tiny little pieces. He defines sensitive as means developing to widely different states depending on the interaction, and wildly different means the blobs of amplitude don't interact. So they set up special situations where there are wildly different final states depending on an interaction with a sensitive thing, and that makes blobs of amplitude, these tiny blobs of amplitude, not interact.
See, that sounded coherent enough for me just to agree with you, even though I don't really understand exactly everything you said.
God damn it!
I mean, we're trying. We're not gonna be quantum physicists at the end of this.
No,
I think my goal for this was never to learn quantum physics. It was to find things in these posts that was more than just like reality doesn't care what your model is.
Yeah.
And so, like, I wanted to find more than that. So, like, the things I'm finding is disillusionments of like previously held concepts that I had. Like the Heisenberg uncertainty principle, stuff like that. I'm pulling those things out of here. These posts talk about like amplitude distributions in configuration space, and decoherence being I guess to me, a more comprehensible process. And the analogy to like thermodynamics and unscrambling an egg was really helpful. There's math involved that I didn't quite get, and I'm glad that he hit the beat a couple of times about the whole like consciousness impacts this stuff, because that's every quantum woo shiller out there, every Deepak Chopra is saying that, right? I also had Claude tell me how well do these jive with like accepted quantum mechanics, and so far it doesn't think that this challenges anything that quantum physicists at large believe. So one of the critiques of these posts that someone pointed out is that like this is just one approach. I think so far these two posts anyway don't conflict heavily with the scientific consensus, and that might just be Claude's innate agreeableness. But I think that at least these two posts are pretty well regarded as far as like being accurate among quantum physicists.
Excellent. Well, I hope we didn't misrepresent and mangle them too horribly, because like I said, I don't know half of what I'm talking about, and I'm starting to have serious reservations about the decision to go forward with this. Oh well, we'll keep trying.
Yeah, we'll do it, and we'll get through it. Give us some feedback. If you guys hate hearing these, let us know, and we'll like quickly skim the remainder. Or if you say, look, get it, figure it out, and try harder, then we'll try to do that too. I'm not saying we will. I'm just saying we'll do it. I'm saying we'll try.
Okay.